Welcome back, everyone. So now we are going to have a panel. As you have learned in today's lecture, that these amazing feats can be achieved with these quantum systems, but they also have this limitation of scaling them to larger practical utility scale systems. And this panel will dive deeper into these questions. And this panel will be moderated by Professor Leonid Rockinson. And it's my pleasure to introduce Professor Leonid. He is a professor of physics and astronomy in the physics department and has courtesy appointments also with the Elmore Family School of Electrical and Computer Engineering. His research explores novel topological superconductor platforms as well as quantum circuits and qubits for using those platforms. So with that, I'll let the mic to Leonid.
Yeah, thank you very much. And I'm sort of slightly changed since they've seen me last time, but as long as my wife doesn't see that, I think it's okay. Let me introduce the panelists and, of course, our guest, Dr. William Oliver, who has joined appointment at electrical engineering and physics at MIT, who just gave a talk, and his research interests include material growth, fabrication, design, and measurement of superconducting qubits. He is a co-founder of Atlantic Quantum and fellow of American Association for Advanced of Science, fellow of American Physical Society, and fellow of IEEE. Please join us. Then another panelist is Dr. Alexander Baltashova, who is Ron at Dorothy Garvin Torres Distinguished Professor of Electrical and Computer Engineering, and she has courtesy appointment in material engineering at Purdue University. She specializes in nano and quantum photonics, metamaterials, plasmonics, advanced optical materials, and machine learning approaches for advancing nano and quantum photonics on-chip circuitry. Dr. Alexander Marr is an assistant professor in the Department of Physics and Astronomy who joined Purdue in 2019. His experimental group focuses on quantum simulations and quantum information science using superconducting qubits. And he also worked on quantum simulation experiments and using ultra-cold atoms when he was a postdoc at Harvard, during his PhD at Harvard. So, please. Dr. Thomas Ross is assistant professor of Elmore Family School of Electrical and Computer Engineering at Purdue University. His research focuses on multi-scale and multi-physics computational techniques, particularly on enabling the analysis and design of quantum information technologies. And also he is working on developing quantum workforce, and he is recognized with several awards for his work. Dr. Zubin Jacob is an Elmore Professor of Electrical and Computer Engineering with courtesy appointment at Department of Physics and Astronomy. His research interests are in the field of quantum optics and including superconducting detectors. Okay, I may, let me, I'm not as important.
You're the main man here.
Okay.
There is a scaling problem with the panel.
We could share. Sure.
Okay, so I think let's maybe start with discussing what are the current bottlenecks in quantum computer scalability, whether it's physics, whether it's engineering, whether it's manufacturing, economics, or maybe the lack of workforce. So maybe you can start the discussion.
Yeah, sure. You know, the bottlenecks, I would say, are all of the things that you mentioned. It's across the board. And it's part of a bootstrapping effort anytime we develop a new technology that, you know, first people at universities have to demonstrate that something is worth putting funding into and that it there's actually a promise there. And then once that happens, of course, then you need to continue to expand. And so that means a workforce. It means, funding, venture capital. The way that I look at it is, if you look at a university, there's lots and lots of departments. And quantum may have started in the physics department. It did. And then it expanded a bit to the engineering department as we tried to make it construct these machines that were invented by physicists. And we still need physics and engineers, but going forward, basically, if this is to be a commercial technology, we're going to have involvement from all across a university, all these departments, whether it's the chemical engineers who know the problems in chemistry or the material scientists who know the problems in materials, and of course, our business school. Because if this is going to be commercially relevant, we need to have people who understand finance and understand marketing and business and strategy. So it's really going to take everybody. And the challenge is to train people to be quantum aware without requiring every one of those people to have a PhD in quantum physics.
You want to help?
Maybe I just would like to add to that before we dive into details of scalability. Just for young people to kind of realize that we are in a unique time right now where the progress in quantum technologies, quantum information science and technology is actually happening concurrently across academia, national lab, and industries. And this is very unique. That's not how it usually happens. Sometimes, you see, okay, there's a fundamental advance, there's a breakthrough in fundamental science that, later end up with getting a Nobel Prize. But then it takes decades before it becomes a technology. For quantum, it's very different, because we are working on fundamentally advancing science and discovering new platforms for quantum at the same time as companies are already pushing for practical platforms. And I think this is very unique. And that's exactly what will help us, I believe, to tackle all these facets of the problems of practical quantum systems.
Maybe since we started a little bit on workforce and we have a lot of students here, maybe some question I wanted to ask a bit later, but maybe it's a good time. What do you think are the most needed skills at the moment for big companies, and where we as educators need to focus, and at what level? Special programs, master level, PhD. What is the most sort of urgent needs in the workforce development for these companies to succeed?
So maybe I can start. I would say that in terms of the workforce development, we've Purdue and of course MIT and many other universities have a lot of online courses as well as coursework that trains students. But I think the big challenge has been most of us, when we studied quantum mechanics or we studied things, we were really looking a lot at maybe the conference photograph that Will showed, and really reading about, okay, what did Debye do and what did maybe Rutherford do, and each of those different things. But I don't know if that's the right way to teach the next generation. Because what would really be needed at this point is quantum technology, and that really requires a lot of hands-on work, FPGA programming. You really need to know a lot about amplifiers, high-speed circuits. So getting to teach them in a new way than the way that we studied ourselves, like we professors, I think that's definitely a challenge, and that's something we are all working on, just making sure that they have the skill sets to succeed in industry and just know a little bit about the fundamentals and the history along the way. So I think that's something that we've been all kind of working towards.
And maybe to add to some of that, there's this concept that people like to talk about a lot with quantum workforce development of the idea of like a quantum aware engineer or, practitioner, and then quantum proficient practitioners. So the bulk of jobs and where there's, having a lot of trouble filling things right now is that quantum aware workforce, people that know a little bit, maybe a kind of quantum class or two, but then they have a wide range of classical engineering skills to do control systems, cryogenics, RF circuit design, all sorts of optical engineering, these kinds of things. And so that's sort of that gap that you see where, we don't need to train every single person with like a physics PhD, for instance, to go build these quantum computers. And so there is then what Zubin's kind of talking about of, how do we kind of create our curriculum in the right way so that we can get people that knowledge that they need in just say like a few classes and then be complemented by all of these other classical skills that we're already potentially good at teaching, for instance.
Maybe just I add a little bit and say that we also have to get rid of this kind of a stigma. Then quantum is so hard. You need a PhD in physics or something, you need a new name for a PhD to be in quantum. And as Tom just mentioned, we need so many different types of skills. And in fact, the Quantum Economic Development Consortium that actually has as members all the companies that have quantum R&D, they're working together with funding agencies like NSF, trying to identify what are the skills that are needed by the quantum industry, and then create those centers that actually shape the quantum education according to these needs. And if you look at the charts of what skills are needed, you would be surprised. It's definitely not like quantum mechanics even. It would be, as you mentioned, cryogenics, it would be, algorithms. And so we need to work together with industries on that, hand in hand.
I'll just also add a little bit. So indeed, like all the others said, you don't need to be an advanced physics student to learn about quantum. You also don't need to be a physicist to contribute to this new emerging industry. So there are also many resources, courses on campus that are tailored towards accessible, quantum phenomena. After all, most of the modern technology, even classical technology around us today, are from developments of quantum mechanics in the last 100 centuries, right? And there are also a lot of student organizations and activities, right? So we have the Quantum Games Club, we have the Quantum Student Organization, a lot of other outreach and student activities. We'll mention the hackathons that we are also participating in a lot. And there are all these opportunities for you to get to know this field, yeah.
Okay, so going back to scalability, as you mentioned, there are a lot of things which go into the system from just quantum process itself to how it's packaged, how it's cooled, what's the outside electronics, what the cryogenics, what are the software. Where you think are the major bottlenecks nowadays for the quantum computer scalability?
Yeah, it depends a lot on the platform, which technology we're talking about. There's some commonalities amongst all of them, but then there are, of course, specific barriers to each one of them. So, for example, a commonality amongst all of them is to achieve some degree of modularity. Right now, all of the different platforms, whether it's neutral atoms, trapped ions, superconductors, and others, have built small-scale quantum computers at maybe 100 qubits or a few hundred qubits. But if we want to get to 1 million qubits, what got us here is not going to take us there, in the sense that we're not just going to keep doing the same thing we've been doing over and over and have that get bigger and bigger and bigger. We know from systems engineering how important modularity is. Make something that is, relatively speaking, small compared to the full system, and then, or a few things that are small, and then connect them together in a way that makes a bigger system operate. That this is this is in the playbook of systems engineering. So all of the platforms need to do that. Specific things, for example, superconducting and semiconducting qubits, what does cryogenics look like at a large scale? It's not, most of these are engineering questions too, because it's not a showstopper to say that if I need to dissipate twice as much power, I just build a twice as big refrigerator. That's not a problem. At some point, I'd like to connect refrigerators together so that if one refrigerator goes down, the whole system doesn't go down, just n minus 1 can keep going. So that's part of what we deal with: fabrication, engineering, material science, lower loss. Right? These are problems that we face. For neutral atoms, it's a lot about laser power. As they want to trap larger and larger numbers of atoms, they need much, much higher power lasers. And they're already pushing the edge. And so that's, as I talk to them, they're talking about larger field of view optics, larger lasers. Trapped ions. Trapped ions, they really would like to do it on a silicon chip, so that means integrated photonics. We have some experts here in integrated photonics. How to direct the signals where they need to go, how to collect the light, right? So there's a lot of these, nitty-gritty technical but very important issues that are platform dependent. And then there are some that span all of the platforms, more at the architectural level.
And kind of to build off of that a little bit, in most of the technologies, there's also some element of kind of like a wiring problem of getting all of the inputs and outputs going, to that small kind of quantum chip, for instance. So superconducting qubits, you see that very dramatically, where if you look at any of the pictures of these dilution refrigerators with the refrigerator off, you get this large chandelier of cables coming down and down and down, and your actual quantum chip is maybe a couple centimeters in size, for instance. You can't even see it in those pictures because of all of the wiring that's there just to send in your control signals, your readout signals to get the information in and out of the quantum computer. And doing that in like a cryogenic environment is very challenging. But the other kind of platforms like trapped ions, like photonic, NV centers, all these other ones, they still have similar kinds of things of getting enough inputs and outputs into these very, very small spaces where the actual quantum computing is happening.
I can add to that, the company that we started out of my group called Atlantic Quantum, that's exactly the problem that we were addressing, which is the number of wires per qubit and how to reduce that, and how to co-locate the control electronics with the qubits. Basically, because that chandelier looks beautiful, but I don't think it's very beautiful. I think it's a real problem. And ultimately, it comes down to cost. What is the cost per qubit? Today, the cost per qubit is something like $1,000 to $10,000 per qubit. And we want to have 1 million plus qubits, all right? That's $1 to $10 billion if I did the math right. And that's a lot of billions of dollars, right? And maybe one is heroically built that way, but that can't be the way that it goes. So reducing the cost per qubit, the control wires per qubit, whether they're wires or laser beams or whatever they are, this is critical if we're going to realize this at scale.
Yeah, so sort of building on that, for example, if we take superconducting qubits, which is sort of I'm more familiar with, and their number-wise scales is about 2.5, depending on what architecture you use with number of qubits. So you hit the limit of about 1,000 wires where you cannot package more. So multi-chip models are, of course, the way to solve that problem in semiconductor technology, except we need to keep power dissipation compatible with 10 millikelvin environment. What would, from your perspective, would be the sort of competing and possible technologies to solve that problem?
Yeah, so the technologies that are candidates to solve that problem, one is multiplexing, brute force multiplexing, which is you send down one signal, and rather than having that one signal address one qubit, you have it go through the entire chip, and you bring the qubits, say, onto or off of resonance with that one signal. That's one. So multiplexing is part of this, and we should leverage multiplexing as much as we can. The second is cryogenic CMOS, and I spent some of my early career at Lincoln working on cryogenic CMOS. And it does work at millikelvin temperatures, at least SOI, silicon on insulator type, but it's still too power hungry, to be honest. It's only in what we call the lowest activity factor applications. Activity factor is how often is the transistor actually switching in the task that it's performing. And if it rarely switches, okay, maybe that's fine, but the dissipation is still too high to have high activity factor. It's not going to replace generators that we have at room temperature, no way. So then the third possibility for co-locating electronics is to use superconducting digital electronics to do that. And this goes by many names, but single flux quantum logic is the main candidate here. Digital, classical, based on Josephson junctions and shuttling flux around. Even that is too high, generally too high power to co-locate electronics, but there's one member of the family called adiabatic QFP, or quantum flux parametron. Sorry for all the jargon. I didn't invent it, I just use it. So AQFPs approach what's known as the Landauer limit for classical information extraction. And so the power per op for adiabatic QFPs is lower than any other digital technology that I'm aware of. That's the approach that we took in Atlantic Quantum.
I'll also expand on a point that's already brought up earlier, which is I think the future of the quantum infrastructure or the ecosystem will be heterogeneous with multiple different physical platforms. So I think it's too early and also not necessarily a bad thing that some of them might require cryogenics that are more scaling at this point and some doesn't, right? We can imagine having super quantum computers at a centralized location to run the most demanding tasks that need more power, more resources, just like our supercomputers today. You wouldn't want to run it out of your garage, but we still have our mobile phones, quantum sensors, communication devices based on other technologies, atoms, optics, that doesn't need that infrastructure, and that are quantum connected. Yeah.
You mentioned like optics in passing, but I'm biased, obviously. And I just wanted to add that I do believe that the photonics and chip-scale photonic technology will play an increasing role in actually connecting, provide the connectivity and this low cost and low power performance for connecting this modular architecture. Of course, photonic quantum computing on itself is very interesting, and it has a lot of promise specifically for scalability as well. So, and yes, I agree, I believe in hybrid or heterogeneous future as well.
So I can add to that. I also have a bias towards optics, of course. And so maybe I'll just frame this comment in a slightly different way. So if you look at classical today, right, let's look at the GPUs, right? If you want to train your large language models, you will need a lot of GPUs, and you also need a lot of training time. So the trend is very clear. If you've looked at, recent press release from Broadcom or NVIDIA, the trend is very clear. I think that the plan for even the classical GPUs is to really go towards, and they're already doing it, optical interconnects just based on fibers. And I think the next generation, TSMC already has these entire kind of fab processes being developed of building kind of optical interconnects in kind of heterogeneous integration layers to have, say, GPU layers and maybe a optical chip layer and connecting all of them. So this is definitely going to happen in the case of existing GPUs. Just having very large number of GPUs for the training is necessary. And of course, there are some issues. You cannot have your entire training time to be very large, and at the same time, you can't have any error in between for your training to break down. Like if Facebook is training an LLM, they don't want it to stop on day 21 if it was a 30-day effort, because even a 30 to 60-day effort is a large effort in terms of how much competition is going on. So what is happening is the companies prefer to use their existing software architectures with the hardware. So a lot of the hardware work is about, even if you build in the optical interconnects, how do you make sure that the software engineer need not know anything about how the entire wiring is completely different? So I think that similar things probably can inspire the quantum work as well. So we have an expert here. I think he cannot comment, but the transduction of microwave signals to optical, right? So it can be done with high fidelity, but it's still something that is more research. How do we build modular architectures to take microwave signals, convert it into optics, and then just get it out of your cryo environment and connect many different cryo systems. So I think there is a lot of commonality that even the classical one is going to have a lot of optical interconnects between the GPUs, and we'll probably see that in the maybe even superconducting platforms or some ion traps and neutral atoms almost for certain.
Maybe that leads us to the next question, actually a bit of a history, right? How the classical computers were developed. We had very small scale desktop computers at the beginning, then we had workstations which sort of were invented to have much more power and we connect multi-user connection. Then we moved back to very powerful home computers, and looks like we are moving now to the cloud again. So it's sort of these back and forth between centralized and so what can we learn from development of classical computers? How for example, density on the chip is increased over time versus modular systems, and where it breaks and doesn't work for development of quantum computers.
Well, I think that for the foreseeable future, meaning 10 or 20 years, that we will be in the mainframe era of quantum computing, right? Where these are very complex machines and they need to be maintained by trained staff, and so these will be machines that we as humans go to, much like in mainframes in the 60s and 70s. Now going to it today means we can also use the internet to connect to it classically to a local classical computer, which then talks to the machine. But the machine itself is going to be quite complicated, need to be maintained, and therefore we will go to the quantum computer. Beyond that, I think it's anybody's guess as to whether these become more personal devices, maybe starting with quantum sensors. But what I do believe is that if we go forward 100 years, I won't be around, I guess most of us won't be around, but in 100 years, I think humanity will look back and say, of course we're processing using quantum, and of course we're sensing using quantum, because the world is quantum mechanical. Just like today we look back and say, of course we're using electronics to do our calculations. We don't use mechanical calculators anymore. It just makes sense. And I think between now and 100 years, and whether it's 100 or 90 or 110, I don't know, but we will be using quantum mechanics to do our computation and our sensing and our communication in conjunction with everything we already have as well.
I just want to add to that, and I am actually repeating what Dario Gil is saying about the future, that we are not necessarily moving like entirely toward the quantum world. We are still going to use classical bits. We are going to use qubits or quantum mechanics. And most likely, and I think for sure, I believe for sure, we will be use neuron as part of neuromorphic computing as well. So this kind of three pillars will be here, and they will be playing synergistically together. And I think, again, as a society and researchers, we will get better and better at deciding or working with AI to decide which tasks should be solved on which machine, whether it's classical supercomputer, quantum, or not. So again, the future is hybrid. So we'll just have to move there and concurrently develop all these three pillars.
It's absolutely true that in 100 years we will still be classical. So we need to interact via classical bits.
Maybe a little bit tangential, adding on hybrid being the future. There are also different modes of operating a quantum computer. I think for classical computers, there was a long time where the most useful applications are actually analog computing. Not digital logic gates, right? Early computers, even till late 70s or 80s, were the most powerful at, for example, calculating trajectories of projectiles. And that's the same in quantum computing. Will mentioned earlier that we think one of the early applications of quantum computers will be for calculating quantum mechanical systems, the world that is natively analog and continuous, right? So there are different ways of operating the system. Of course, eventually, we want to go to the fully quantum error-corrected regime, but we all know that's probably going to be at least decades away. In the meanwhile, are there problems that can still be of commercial advantage that perhaps doesn't need the same mode of operation or the same requirements?
To kind of build off of that in another kind of related direction as well, with kind of the analog part in particular, this is, again, one of the spots where even though, the types of quantum computers that people like IBM or Google or a lot of these companies are going towards might be kind of referred to as like a digital quantum computer that's using qubits, and it's always projecting things back into that 0 and 1, and has that universal gate set, like Will was talking about in his talk. The actual control of those still has these, superposition states over a continuum of the planet Earth, plots that Will was showing. And so the kind of control of these systems is still more analog than digital. And so that does kind of cause things to be very different in terms of how we think about scaling up the systems in comparison to how we were able to develop and kind of replicate classical computers to like larger and larger and larger bit counts very fast.
I want to ask a question related more to the manufacturing, maybe, and uniformity. In superconducting qubits, having almost identical Josephson junctions throughout the chip is absolutely crucial, and different companies solve that problem differently, each of them building their own primarily fabs to sort of deal with that problem. It doesn't presumably exist that problem as strongly in atomic systems because atoms are the same. But do you think companies are already close to use some well-developed commercial fabs, or that would be a niche which requires very special developments?
Yeah, so I did a lot of work on this at Lincoln Lab, where they had a conventional CMOS fabrication facility, trusted foundry. And I found that to be quite advantageous in the following way, that there were some fantastic engineers and material scientists there who cut their teeth on CMOS, and they knew exactly what to do to develop new processes. Now, their intuition was almost all wrong, to be honest, because they thought, okay, I can solve this problem by annealing at 400 degrees C. And then you say, well, you can't do that. And they're like, oh. So what they knew for CMOS didn't apply directly, but that wasn't what was important. What they knew how to do was to develop new processes. If they knew what the boundary conditions were, they knew what to do to turn the crank, how to design the experiment, how to test, and close the loop and fix the problems quickly. That's many of the people had worked in the late 80s and 90s, in fact, on CMOS, and that was exactly the same problem that we had then: uniformity, yield, et cetera. So I think these people who work in foundries are critical to the advance, not just of superconducting and semiconductor qubits, but also to trapped ions and neutral atoms, whether it's integrated photonics or chip traps. This is very important. On the other hand, if you think back to the 80s and 90s, it was almost a mantra that if you're going to be a serious designer of chips, you have to have the in-house fabrication facility, because that cycle was so important, that turnaround time and the development, because we didn't have all the answers at the time. I think quantum is in that space now, where we need to have that quick turnaround and flexibility and feedback. There's not a market yet. If I wanted to start a company tomorrow to say, be the foundry for superconducting qubits, there is even a startup to do that. Who's going to buy those chips? And are they going to buy them in a volume that allows me to have the staff and the equipment and the capital expenditures and everything that needs to happen to run a foundry? my belief is probably it's not there yet, right? Which is why the existing foundries like Skywater or Lincoln Lab Foundry or the IBM internal foundry or the Google internal foundry, these are all very important at this stage because although they each have different funding models, they actually, close the budget at the end of the year and they don't go broke. Yeah. So I think we do want to use foundries eventually, but it's a very expensive endeavor to have a foundry which focuses only on quantum. They need to have other business and generate revenue through more conventional approaches as well.
I just wanted to add to that, and definitely, we are in early stages for the entire technology, and as a reflection of that, also the fact that I don't think that in the near future we will converge to a single platform. And that means that it's not like with silicon-based technology, where we kind of early on we will realize, okay, this is, that's the way to go. That's the material, that's the technology, and everyone now it's, silicon-based chips, right? So we are far from that point, and there are so many platforms that are being developed in parallel. Going back to foundries and the kind of the possibility of actually start even testing whether it would be feasible to scale it up, and so photonics again, integrated photonics, and I think one of those approaches, which is even now is foundry ready. So with Vlad, we're working on this single photon emitters that are already sitting in a platform that has a PDK, the process development kit for integrated photonics. And silicon nitride is a go-to material in the chip scale industry. So foundries are kind of, in this specific example, they are closer to give it a try. Compared to, let's say, other platforms. And again, I think we just have to push in all those directions to see what's come next and what this specific platform would be best for.
Yeah, and if we have dual-use technologies like a lot of the integrated photonics, then your customer base is much larger. You don't have to only sell to the PsiQuantums and the Xanadu's of the world. Anyone who's developing, say, GPUs and wants to have optical interconnects between them would benefit from this type of technology, and therefore, okay, this is a business, and as a foundry, I would get into it. Yeah.
Okay. During the talk, you've shown this beautiful work by Google, where they compared different logical qubit connectivity. But that has been done on a just general chip, which they had just some number of qubits, I think below 200 at that time, where they dedicated, okay, either we have these qubits we call a logical qubits, or these number of qubits we call logical qubits, or some larger collection. So that's basically how that data has been obtained. Clearly, sort of, if we want to develop more modern platforms, these logical qubits presumably need to be the base of the hardware architecture and then grow up from that. So are we at that point, or we are not yet at the point where these logical qubit sort of architecture is mature enough so we can start build from designing from the logical qubit level up?
I think in the abstract we are at that level. In fact, on the theory side, it's done. This abstraction, if you assume that we are at the logical level, almost all work on algorithms assumes that we have good qubits, and by good we mean logical qubits, right? Protected. So I think that abstraction is already there. On the hardware side, it's midstream. Right. I spoke before about modularity, and these start to become systems questions. As a systems engineer, I'm pretty excited about that. What's on the menu of options that I have available to me to create a system? Let's define that system and build it. What has been demonstrated is basically a memory by Google. Other companies like Quera, Quantinuum, have demonstrated logical gates between logical qubits, but which is very important to demonstrate, but they weren't necessarily below threshold. They didn't show the threshold scaling. So we're very much midstream, right? And I think that, within the next 5 years, you will start to see, okay, maybe what you described, which is architectures involving multiple logical qubits with the systems engineering intending to accommodate them, right? Not building logical qubits from a bunch of physical qubits, but actually designing systems because we know that we need logical qubits as the constraint.
I think quantum error correction has been abstract and just in theory for quite a long time. Most of the knowledge we know about quantum error correction was developed long before we had any physical qubits. And I think this is the first time in history where now the algorithm needs to think about the hardware, and the hardware development needs to be aware of the quantum error correction algorithms as well. I think it's not an accident that most of these experimental demonstrations of beyond even or beyond thresholds demonstrations all happened in the last 1 or 2 years, because we're learning so much between hardware, algorithm, the software and firmware in between, and from each other, all the different platforms. So I think this is an exciting time where we already start to see hardware designs, architectures that are aware of the different algorithms that are around there, and algorithms that are co-designed with the hardware to be more efficient. And I think that's the way forward. And also, Will had it in his slide, but didn't have time to get into, which is there was also the passive, or I should say more autonomous mode of error correction, hoping that eventually some of this active measurement and correction can be moved to the hardware level or the firmware level, so that you have to, you only need less resources for active control from the outside.
Talking about the control, right, you had a photograph of Huang and talking about quantum computing, and I know that NVIDIA also, they are thinking of integrating quantum computers with their clusters. How much you think AI will play the role in error correction or in general development of quantum computers, I don't know, algorithms or control and detection?
Yeah, I would say it's already playing a role. Certainly in our lab, and I guess talking with Sasha earlier today, and in her lab too, it's, students don't want to have to sit there for 2 weeks trying to calibrate, 400 parameters when there are better ways to do it, right? And so reinforcement learning, machine learning by extension, are techniques that we're already using to calibrate our chips and make them work better. The inference that needs to be done for quantum error correction to understand where an error occurred, the type of error, this also, I believe, will be improved with reinforcement learning and machine learning. And in fact, my guess is that in those syndrome measurements that are coming out, from the referee's qubits, there's more information than just an error occurred at this qubit. We just don't know what it is yet because we're not inferring that information yet. And I think that machine learning will tell us that there's a lot more in that stream of data coming out than just the yellow, red, or green card.
Yeah, I just want to add on to that because I am such a big believer in machine learning, and especially in crossroads or intersection of quantum and AI at large. And I probably make it stronger. I say not only machine learning can kind of advance and help, but I believe it will be foundational in future. So for calibration, for measurements of devices to start with, for prototyping, at actually single step of the process, starting with fabrication and reliability, right? How to predict, how reproducible your fabrication is, how scalable that is, what is the tolerances, and going to calibration, controlling of your qubits, reading out the state, right? And improving the fidelity with which you can read the state. And the error correction. What if we find patterns right? If we find this is what you said, right now we're just, we're measuring or something happened, we try to correct it. But we should be able to look at the entire picture of what's going on and predict and correct for that by defining those patterns. And this buzzword of digital twin everywhere, and the digital twin for quantum computation is also going to, I think, be developed together with AI that could help us, as I already said, at every step of the process.
Another spot where we haven't maybe touched on too much with like machine learning or AI helping is in the actual kind of physical layout design as well for these, like for superconducting qubits especially, for instance. Each qubit does have kind of similar features to it, but it has to have different kind of distinct like resonant frequencies that you're targeting, and you're designing other electromagnetic resonators that couple to these qubits as well to kind of interface with them. So you're having to design millions and millions of resonators. Each one has a physical layout that's slightly different from the others, but they're all still very similar in shape. And so having like an actual engineer sitting there trying to design all of these is incredibly, prohibitive. It's one of those applications where, again, you could actually train up an AI or machine learning kind of model to help with that design process and make that a lot more turnkey for some of those things.
Leonid, maybe the only one small thing that I would add to that, I completely agree, is maybe I've always been biased to theory, as you know, so there's actually been a lot of work on understanding correlated quantum noise in systems. But then those theories were, just ended up being just theory or curiosities for a long time. And one of the things which kind of comes to my mind as Will and Sasha are talking about kind of AI and control is, those referee qubits, they have more information than just what went wrong. And especially if you start scaling it, then it's the correlation between the referee qubits that can really help that. And so there is this big field of studying open quantum systems with correlated noise that existed, but it was just done for theoretical interest. I wonder if that would be of practical engineering use, maybe in the near term.
And I think it really would be because, again, there's some very nice papers looking at some of these things for certain superconducting processors, for instance, where, again, whenever people are making these kind of surface code implementations, they're sort of assuming that a lot of the errors are uncorrelated. And then you go and you look at some of the error signatures that you get on these devices and you see, oh, shoot, these errors are correlated. And so, again, being able to use some of these, surface code prototypes as maybe a little bit like a test bed to kind of investigate that noise signatures and the correlations more deeply might, again, help us learn more of what's actually happening in there.
Yeah, I can see Vlad is looking at me and he's always like jumping on the chair. And I think what he wants me to do, if I read your mind, and I do, to actually mention that algorithms can also, this is our very recent work from our collaborative project on actually predicting decoherence in quantum system. And I think this is extremely exciting. So led by our student Pranchu, it's the one that really can help you, well, basically to predict the evolution of the quantum system. So now we tested this is just for emitters, but obviously this is something that we can apply broadly to quantum systems. Very exciting.
And before we wrap up, I want to maybe give a more provocative question to you is, do we really have enough applications for quantum computing to justify the investment frenzy?
Well, I think that if you look at the history of classical electronic computing in the 50s and 60s, it started with scientific computing almost entirely, right? And I think that quantum computers similarly will start with scientific computing. Whether it's worth the investment frenzy or not, I think will be determined by what the ultimate commercial applications are. But in the near term, those applications will be related to scientific computing. You go to these B2B conferences and business to business, and you get all sorts of people just saying stuff that's really hypey, like quantum computers are going to solve climate change. Okay, quantum computers are not going to solve any problem like climate change. What quantum computers will do is simulate a material system or simulate a chemistry and give us a higher quality solution than we otherwise got. And then it's going to take engineers who are very clever to take those results and then make a better battery and then have an impact on climate change. So I think it's hard to say whether it will justify the frenzy at this point, but I am comfortable saying that it will do scientific computing. And if we are smart enough to take the answers that come out and do something useful with it, then I believe it will be commercially useful.
Okay, let me thank the panelists, and let's thank the panelists.
You can take questions from the audience.
Oh, anyone has questions from the audience? Oh, okay.
So you guys all mentioned that scaling qubits is an engineering problem. Is it just an engineering hard problem, or is it a DARPA hard problem where DARPA should be investing in it?
Of course.
DARPA should absolutely be involved.
But you got to convince us why and how.
I know the Heilmeier criteria.
Any?
You mentioned using ML for predicting decoherence in quantum systems. So I'd like to ask you, when is a quantum system most susceptible to decoherence?
You're asking when the quantum system is most susceptible? Well, it depends on the environment, that your quantum is sitting in. And again, there is always a trade-off, right? You want to have a pure quantum system with a purely defined state and long decoherence. You want to isolate it completely from the environment. But then you can't, because you have to control it, right? It's all about control. So it's a trade-off of what kind of environment you design around your system. And add to that, you want it to be practical. So let's say if it's a single quantum emitter, it is sitting on a chip, and it has to be connected to cavities and waveguides and couplers. And so this environment and the temperature of operation and everything else defines how it behaves and how bad or how good your decoherence properties will be. And again, since this is such a complex environment, it's not easy to actually single out all the mechanisms to predict it at control. So we need some clever AI algorithms to actually help us to do that.
And maybe one of the other kinds of things to kind of mention on that is when we think about like classical computing, for instance, it only has one kind of error really. Your bit can accidentally flip from like a 0 to a 1 or vice versa. Whenever we're talking about qubits, though, you're sensitive to both bit flip kind of errors, but you can also have the phase changing to you. And so there are times where maybe in a quantum algorithm, you're in a fortuitous position where you're not having phase information encoded in that qubit, and then it's less susceptible to that type of noise, but you can't really rely on that. And so there are hardware engineering efforts, though, that are focused on, well, maybe I can't design a qubit that's just uniformly better at all of those error types, but if I can suppress like just the phase error really well, then maybe I can have a more efficient like error correcting code that's just focusing on that remaining error sources. So there's different kinds of ways to play with that.
Hi. So first of all, thank you for the lecture. Thank you for the panel. My question goes as follows. As it might have been suggested, there is currently a big interest in quantum from the federal government, from different actors that are putting money into it. The question for the panelists is, are you concerned that we're gonna run out of fuel in the next few years? Do you think that we need, is there something we need to come up in the next 4 or 5 years to continue this momentum? And if we run out of these alternatives, how do we pivot? How, like 5 years down the road, 10 years down the road, where do you see this evolving into?
Yeah, there's always a danger of a quantum winter. And AI had several winters, as you may remember, and there was a quantum winter around 2006, as I remember, and maybe there were others. I think that a couple things. One is that because of the cryptologic application of quantum computers, there has been a consistency in the funding, more or less. So there was a winter, but it was like winter in Hawaii, right? It wasn't, wasn't winter in Canada. So the funding went up and down, but we always knew in the back of our minds that, okay, we really need to do this because of Shor's algorithm. With the advent of post-quantum crypto systems, okay, that's going to take 5 to 10 years to really get in place. But once that is in place, it won't go away because of harvest and decrypt later, but it, we'll all breathe a sigh of relief. And at that point, I think we need to have made enough progress on the commercial side so that that now takes the reins away from, say, Shor's algorithm and the motivation for funding there. If we don't do that, then I think our winters may be a little further north than they have been in the past.
More questions?
Okay, first of all, thank you for the panel session. You've really emphasized the importance of quantum error correction, especially at the hardware level, for us to be able to scale this technology. And there's this popularizing research suggesting that black holes, through the quantum mechanism, they do not destroy all the information that enters it, but rather encodes it and stores it at the surface of the black hole. Do you think studying black hole can actually inform us about error correcting codes, or if this is a mere hypothetical?
That's a great question. That's a great question. And you want to comment?
Yeah, so this is a very deep question, and it's a really wonderful question. And I'm not an expert. Maybe Leonid or somebody else can comment. But it does turn out that there is a similarity between the surface error correcting codes that have been developed and the theories of gravity near a black hole and quantum gravity and so forth. And there are many theorists who have spent a lot of time understanding, let's say, black hole information rather than maybe black hole radiation is well understood. Think of it this way, that light doesn't escape, but there is some small radiation, thermal radiation that escapes, which is known as Hawking radiation. But people have studied more details of the information that escapes from the boundaries, and that has informed error correcting codes. So it's very esoteric research, but you are right, it does inform some of this. The inspiration for practical error correcting codes also comes from studying such problems. That's a really nice question. Yeah.
And maybe it will go the other way around as well. So you asked whether studying black holes could help, and I think it would be the other way around, that actually developing quantum systems and quantum information science further will help us to understand more about black holes.
Great. Any other questions? Okay, if not, maybe one more.
First of all, thank you for a wonderful presentation. So you just talked about the scalability, and my question is related to the role hardware manufacturing plays in it. So can we really reuse the bulk of CMOS compatible manufacturing powers established for the classical semiconductor devices? And if yes, what are those manufacturing technologies? Also, do they need to be extended and scaled to accommodate the growing demands down the road? And also, what are the materials that play significant, crucial role in those devices?
Yeah, we absolutely can leverage that. And that is one advantage when we think about the time scale over which quantum computing will advance. We don't have to relearn all that was learned as we developed CMOS. Well, started out as BJTs and then emitter coupled logic and then eventually CMOS. But at the same time, we can't use it necessarily exactly as it is, right? So I don't know the exact number, but maybe 75% is reusable. We need lithography, we need etch. But as I mentioned before, some of the standard tools or tricks in the playbook of CMOS fabrication just don't work, for example, with superconducting. In the case of integrated photonics, often the approach is there, but the level of loss is still too high in conventional foundries because, those foundries solve problems that their customers have. And if the customer says, I need my loss to be in some units at the 99% level, they will target 99.1%. And they'll say, okay, I met what you need. And then quantum folks come along and say, well, actually, I need 3 nines. Okay, so then we have to further do process development. But the tooling, right, is largely the same. Now, we may need some new tools as well along the way as we understand what is required. And that's not unlike in CMOS. At some point, they had to have introduced copper into the process, right? That took some time, and we had to be careful because copper used to be a poison, right? Okay, but now we need it. Okay, we'll figure out how to make it compatible with CMOS fabrication, and now it is. Hafnium oxide, right? So I view, at least from the superconducting and the semiconducting side, and probably also from the integrated photonics side, that it's more along those lines that we do need to make changes to it, but it's not a revolutionary change. It's something that needs improvement in innovation, but not necessarily an invention. At least that's the hope. We'll use that as much as we can. If we do need to invent something new, we will.
Yeah, and exactly. So we acquired so much knowledge on, for example, how to optimize the materials and how to get, the purity or the quality or the crystallinity to the extreme, that this is obviously something we can use. Another thing to mention is heterogeneous integration, which also will be very important for a quantum system because we know that it's not going to be, will be dissimilar systems. Again, you want to integrate so many things, and all this integration skills and expertise, that's something that we can also leverage.
Right. Maybe time for just one last question.
Hi, everyone. It was great to hear to everyone today. I'm Sid. I worked at NVIDIA last year, so Jensen and I, with my team, we had a talk on quantum computers, and we are really optimistic on this. So my question is, which sector do you think would be the first adopter of quantum computing? Like autonomous vehicles, robotics, or molecular biology. So what are your views on this?
It's a good question. I think that, the first commercial applications will likely be surrounding either optimization, in which case could be anybody, everybody's optimizing, or it's around simulation of a material or a chemistry. And I think I'd spoken to some people earlier today, but the pharmaceutical industry is very well matched to the quantum computing timelines because pharmaceutical companies will spend $1 billion and spend 10 years to develop a drug, run it through trials, only to find at the very end, actually, it's ineffective and the time and the money is lost. And so if I or you or someone goes up to them and says, hey, a quantum computer might be able to help, but its timeline is more like 5 or 10 years, they're like, great. Sounds like drug development, right? And, well, it's going to cost a lot of money. They'll be like, well, great, we do that every time we develop a drug. So I feel like it's very well impedance matched to the problems in the pharmaceutical industry.
And I just want to go back to first application, as I mentioned, will be scientific, most likely. And we can also maybe say that, the first quantum computers will help you to design a much better quantum computer by discovering the materials. So, and if that's the goal, it's a valid one,
All right. Thank you, everyone. So thanks the panel and the moderator.